What's up guys, and welcome to this third video. In the last video we did an example where I stopped at guide number 7 and used a, let's say, a visual approach to determining whether we needed to go on to guide 8. But another way that we could have done it is actually used an analytic approach and actually went on to do guide number 8, and we would then figure out that there's no solution. Okay, so what I'm actually going to do is I'm going to run that process as well in this video before jumping into the next question. Okay, so guide 8, what we need to do is we need to change S to I omega, or let S equals I omega. So we let S equals I omega and try solve for K. So the equation that I'm going to use is this equation right here. Equation right here. So let's get that down. That's K equals minus S plus 3, S plus 7 all over S plus 2, if I'm not mistaken, S plus 2. Okay, so let's just do this in terms of S first of all, so that we get it into a nice format first. Okay, so we can say that K S plus 2 is equal to minus, and here we go, so we have S cubed, let's put brackets around there, or let's not, okay, no, let's keep it there. So it's going to be S cubed plus, what's that, 10S plus S squared plus 21S plus 0, okay, whatever. Okay, now what we're going to do is we're going to let S equals I omega, so we're going to have K I omega plus 2K is equal to minus I omega cubed plus 10 I omega, it's actually a minus, squared minus 21 I omega. Okay, now I'm going to equate reals. Okay, so I'm going to say, okay, let's actually get this. So that's going to be minus I cubed, okay, which is I omega cubed, minus I squared is a minus, so we're going to get plus 10 omega squared minus 21 I omega. Okay, now I can equate reals. Let's see if I can move this down. Okay, so now I'm going to equate the real parts from the left-hand side and the right-hand side. Okay, so what I'm left with is 2K, so that's that done, is equal to 10 omega squared, that's that done, and then I'm going to do the imaginary. Okay, the imaginary is K omega is equal to omega cubed, so it's minus 21 omega. Okay, now I can say that K is equal to 5 omega squared. So this becomes, what's it, 5 omega cubed equals omega cubed minus 21 omega, substituting K into there. So what I can say is that 0 is equal to 4, let's bring this, so it's 4 omega cubed plus 21 omega equals 0. Okay, so factorizing this, I can take out an omega. So I'm left with 4 omega squared plus 21 is equal to 0. So omega, as we can see, okay, omega equals 0, we don't really care about, or 4 omega squared equals minus 21. And this will give us imaginary solutions. Okay, so there's no real values of omega, therefore the locus does not cross the imaginary axis. Okay, so that's yeah, that's basically what we needed to do to make sure if we wanted to do it analytically, but again, you could have just looked at your root locus and worked off of that. Okay, so moving on now to our second example. So let's go and let's do our second example. Okay, so we have example 2. Okay, so example 2 says the control system has an open loop transfer function g of s h of s is equal to k over s s plus 2 s plus 5. Okay, so as per usual, we want to get it in our standard format, which is 1 plus k times 1 over s plus 2 s plus 5 is equal to 0. Okay, guide 1 tells us that it's symmetrical, and we don't care too much about that. So we can now move on to guide 2 and calculate where our poles and our zeros are. Okay, so the zeros are at the top. So if we look at the zeros, we have no zeros. Therefore, z is equal to, or the number of zeros is equal to 0. And if we look at our poles, we have poles at s equals 0, or minus 2, or minus 5. Therefore, p is equal to, and we have 3 of these, so we can say p, or the number of poles, is equal to 3. So p minus z is equal to 3. Okay. And now we can look at guide number 3. Guide number 3 tells us that we have the number of poles equals to 3. Therefore, we have 3 paths. Okay, and on the paths we have no zeros. So all the poles. So we can say that all the poles end at infinity. Okay, so let's get to a nice quick sketch of what's actually happening. Let's see, there we go. Let's get a nice sketch going. Okay. So we have our real axis, and we have our imaginary axis. Okay, and let's go with every 2 blocks again is equal to 1 unit. Okay, I think that should be enough, and the same scale, using the same scale on the imaginary axis. Okay, so now let's plot our zeros. Okay, so we have no zeros, so there's nothing to plot, but we do have some poles. We have poles at 0, minus 2, and minus 5. So that's our first one right there, 0. Minus 2 would be here, and minus 5 would be 1, 2, 3, 4, 5. Minus 5 would be right here. Okay, so we have our 3 poles, and then we can go on to guide number 4. And I think guide number 5 actually. Let's see, guide number 4, no, just guide number 4. We can use guide number 4, and we know that the root locus must exist between these two. So root locus must exist between these 2 poles and must exist on the left hand side of an odd number of poles or 0. So it must exist here as well, and this goes on to infinity because there's nothing to stop it. Okay, now we can go on to guide number 5. So this we've drawn on. Okay, so what does guide number 5 have to do with? Guide number 5 has to do with our breakaway points. Okay, so to calculate the breakaway points, we say dk over ds is equal to 0. So we need to start off with what we have, which is 1 plus k, 1 over s plus 2 s plus 5 is equal to 0. So we can say that k equals minus s plus 2 s plus 5, skipping a couple steps, and so we can say that k is equal to minus, let's keep the minus on the outside, we can say that's s cubed plus 7s squared plus 10s. Okay, and now we can do dk ds, dk over ds, so we're differentiating k in terms of s, so we're going to keep that minus right there, and we're going to say that's 3s squared plus 14s plus 10 is equal to 0. Okay, so we can drop that minus, and we can say that 3s squared plus 14s plus 10 equals 0, and we can then solve for this, plugging into our calculator 3, 14, and 10. So we get that s is equal to minus 0,8804 to 4 decimal places, or s is equal to minus 3,7863 to 4 significant figures. Okay, so now we have to figure out which one of these is most applicable. So we have our root locus already. Let's just number these. So this is 0, this is minus 2, that is minus 5. Okay, so our first point is, and we know that it needs to break away somewhere here, right? It needs to break away in here, because this already goes to infinity, so it needs to break away between 0 and minus 2. Okay, logically, just it needs to break away there, because we already have one of them going to infinity. So minus 0.8804, that would fall somewhere here, which would be between 0, so let's say it's right there, between 0 and minus 2, and the other one is minus 3, which would be, or minus 3.7, minus 3.7 would be somewhere here, which is not on our loci and therefore doesn't make sense for the breakaway point to be there. So this one is not applicable. And so we can say therefore our breakaway point, okay, let's actually figure out what the value of k is. So what we can say is k is equal to minus s cubed plus 7s squared plus 10s, and we say that k at s equals minus 0,8804. Okay, so what we do is we get minus 0.8804, and we plug that into where we see the s's. That is a 10, and we get that k at s equals minus 0,8804 is equal to 4,0607. Okay, so to summarize, therefore our breakaway point is at s equals minus 0,8804, where k equals 4,0607. Okay, and let's put a nice block around that so we don't lose it. Okay, so that's an important point right there. Now we can move on to guide number 6, which now has to do with our asymptotes, right? So guide number 6, let us use the first rule now to work out the angles at which they approach. So we're going to say theta equals n 180, theta equals n times 180 degrees divided by p minus z. Okay, and we know that p minus z is equal to 3, so that would just be p minus z came out as 3, so that's going to be n times 60 degrees, okay, where n equals plus or minus 1, plus or minus 3, and so on. So we're going to start off, we know we're going to have to do this for, we need at least 3 asymptotes here because of our number of paths, so we need to do this at least 3 times. If we didn't know that, then we could just keep doing it until the terms repeat. but let's go with the first one. So for the first one, we have a 1, which would be 60 degrees. The second one would be minus 60 degrees. And the third one would be 6 times positive 3, or 60, which is 180 degrees. Okay, so let's just sketch out what it would look like. Basically, if we went again, we would get minus 180 degrees, which is the same as 180 degrees. Okay, so if we plot out very quickly what it would look like, so we're measuring from this axis, so we have 0, 90, let's see, 0, 90, 180, and then 270, so 60, let's say 45, 60 would look something like that, minus 60 would look something like that, and 180, so that looks along there, and along 180. So this is 60 minus 160, 180 degrees. Okay, so that's what our asymptotes should look like. Now we just need to find out where the asymptote actually lies. So for that, we go on to guide number 7, and we say that the centroid is equal to the sum, the centroid of the asymptote is equal to the sum of the poles minus the sum of the zeros, or the s values of them, over the poles minus the zeros. So we already know the poles minus the zeros is 3, and we're going to take the sum of the poles, which is 0, minus 2, minus 5. So we have 0, minus 2, minus 5, minus 0, basically because we have no zeros. So we get minus 2 minus 5 over 3 is minus 2, 3, 3. Reoccurring 3, 3, 3. And so forth. But we'll just go to 2 decimal places. So now we know where that lies. So let's go and put that in. Let's do it in black. So minus 2.33. So this is minus 2. Minus 2.5 would be here. Minus 2.3, let's say, is right here. Okay. So now ideally we would use a compass and measure 60 degrees, but I think I have limited access to things like a ruler and a compass. Let's see if I can figure something out, or we're just going to have to guess it. Yeah, I think we're going to struggle. So let us just do some guesswork. Okay, so 45 is around there, so let's say 60 would be a bit steeper than 45, so it would look something like that. But like I said, ideally what you want to do is actually grab a compass and a protractor, or and a ruler, definitely a ruler, and just get a nice 60 degrees. Okay, so it would look like that, intercepting mostly in the same place. Okay, this bottom one looks a bit not too great, but you guys should have it a bit more accurate. And then this going along 180, you won't really be able to see it, but it's along this line right there, along 180 degrees. And let's just label it 60 degrees and minus 60 degrees. Okay, so in this case, now what's going to happen is this is going, it breaks away right here at the point we calculated, and it's going to go up like this somewhere and cut the axes at some value and go along to infinity along that. Okay, so what we want to do is try to figure out where it cuts it. So to do that, we go on to guide number 8. Okay, and guide number 8 says we let S equal I omega. Okay, so let's figure out which equation we want to use. We can use this one right here. So K equals minus S cubed plus, let's see, plus 7 S squared plus 10 S. Okay, so once we have that, now let us go and K equals minus, and we're putting in I omega now. So that's going to be, let's keep the minus outside, I omega cubed, actually let's pull the minus in, minus 7i omega squared minus 10i omega. So then let's multiply this out, so that's going to be k equals, so that's I cubed, which is just I, or minus I, so it becomes omega cubed, I omega cubed. I squared is just minus 1, so we're going to get plus 7 omega squared minus 10 I omega. Yeah, that looks good to me. And now we're going to equate reals and imaginary. Okay, so the reals, so k is equal to 7 omega squared. That's as far as we need. We got that, we got this. And then we can say 0 is equal to omega cubed minus 10 omega. So we can pull out an omega, so we can say that omega equals omega, 0 equals omega squared minus 10. So omega equals 0, or omega equals taking the positive value, square root of 10. Okay. Yeah, the square root of 10. So plugging that back into this equation right here, we can say that k equals 7 times the square root of 10 squared, so that's equal to k equals 70. Okay, so we know the value of k, and the value of s, remember we let s equals I omega, so s equals I times the square root of 10, which is equal to, let's see, the square root of 10 equals 3,1623i. So this again is our important point. Okay, so what we have is 3,16. Let's go and mark out 3.16. So that's 1, 2, 3.16 would, let's say, be here. 3.16, and same on the negative, so that's minus 1, 2, 3.16 is there. So it breaks away at 90 degrees, nice and perpendicular, and then goes towards the asymptotes. So it would look something like that. Okay, so that's what this root locus would look like. Let us go and label some of the important points. Let's label them with red. Okay, so our important points are s equals minus 0,88 at the breakaway. So this point right here, s equals minus 0,88, and k was equal to 4,06 here. At this point right here and this point right here, we know that k was equal to 70 and k was equal to 70, and s was equal to 3,16. So here s equals 3,16 I. I hope I had that I in, because it needs to be I. I did have that I in. Okay, and over here s is equal to minus 3,16 I. Okay, so some of the questions that can be asked of you guys is where, for what value of k would the controller be stable, and that is any value where k is less than 70, because after 70, after k equals 70, we have it going beyond the imaginary axis, which would make it unstable. So stable for k is less than 70. If that was something that you guys were asked for. Yeah, I mean, that's this question done. I hope you guys found it useful. I hope going through the guides makes sense and you guys are able to follow. Yeah, that's the end of this video, and I think I'll be doing one more example. So thanks for watching, guys.